Organic molecules are primarily formed by carbon atoms linking together a property known as catenation via single, double, or triple covalent bonds. This fundamental bonding ability allows carbon to create a vast and diverse array of structures, ranging from open-chain skeletons to closed-chain rings, and complex aromatic structures. Due to this remarkable structural diversity, organic compounds frequently exhibit isomerism, a phenomenon where molecules possess the same chemical formula but distinct properties. Structural isomers are molecules that share the exact same molecular formula but differ fundamentally in how their constituent atoms are connected to one another. Geometric isomers, on the other hand, feature atoms connected in the identical order, but their spatial arrangements are clearly different because the normal rotation around a carbon-carbon double bond is highly restricted. This restriction prevents the spontaneous conversion between isomers under standard conditions, resulting in distinct cis configurations where similar functional groups are located closest to each other and trans configurations where similar groups are positioned furthest apart. Finally, optical isomers represent a specific form of stereoisomerism characterized by two molecules that are exact mirror images of each other but cannot be superimposed. These non-superimposable mirror images form a pair of enantiomers, a situation that typically arises when a central carbon atom is bonded to four completely different groups. In experiment 2, we are examining geometric and optical isomers. In our models, the black pieces represent carbon, the white pieces represent hydrogen, and the red pieces represent chlorine. First, we build ethene C2H4. This structure features two central carbon atoms connected by a double bond, with each carbon bonded to two hydrogen atoms. When I attempt to rotate the carbon atoms, the double bond strictly prevents any twisting. As shown in the drawing, all atoms lie approximately in a flat plane. Moving to our next molecule, we have ethane, C2H6. Here, the two central carbon atoms are connected by a single bond, and each carbon is attached to three hydrogen atoms. Because it only has a single carbon-carbon bond, we can easily and freely rotate the atoms. Here is the drawing. Next, we construct ethyne, C2H2. This molecule consists of two carbon atoms linked by a triple bond, with one hydrogen atom at each end. All atoms align perfectly in a straight line. Just like the double bond, this triple bond restricts all rotation. Here is the planar drawing for ethyne. Measuring the distance between the carbon centers across our three models, we arrange the bond lengths in increasing order. The shortest is the triple bond, followed by the double bond, and the longest is the single carbon-carbon bond. Now we will modify our ethyne structure. We substitute one hydrogen atom for a red chlorine atom on both models to make chloroethene. Tossing them freely and comparing them, these two models superimpose perfectly. There is only one geometric molecule for this formula. Here is the drawing. Next, we change the structure again by adding a second chlorine atom to the exact same carbon atom on both models. This gives us 1,1-dichloroethene. These models superimpose completely and represent the exact same molecule. Here is the drawing. Finally, we switch the positions of the atoms so there is one chlorine attached to each carbon atom to form 1,2-dichloroethene. In one model, the similar atoms are closest to each other, forming the cis isomer, and in the second model, similar atoms are furthest apart, forming the trans isomer. As you can see, they cannot be superimposed, proving there are two distinct geometric isomers. Here are the drawings for both. For a molecule to have geometric isomers, it must have a restricted double bond and each carbon must be attached to two different groups.
We constructed two identical models of bromochlorofluoromethane, CHFClBr. We used different one-prong colors for the halogens. Chlorine is red, bromine is blue, and fluorine is green. They are superimposable. Then we rotate one model to become the mirror image of the other. The molecule can't be rotated to turn into the mirror image of the other, which means that the molecule is chiral. Next, any of the two atoms were swapped on one model. Both models were thrown down and picked up. They are not superimposable because they are different molecules. Hence, for the formula CHFClBr, there are two different molecules which are the mirror images of each other, called enantiomers. This is the drawing for the mirror image pair. The first two bonds lie in the plane of paper, which are the smooth lines, and one of them is vertical. The third bond comes out toward you, which is the thick wedge, and the fourth bond goes away from you, which is the dashed wedge. Next, both models were converted into CH2FCl by replacing Br with 1H. They are superimposable because they are identical. There is no second molecule for CH2FCl because the carbon now has two identical hydrogens, so it has a plane of symmetry, which makes it optically inactive. This is the drawing for the mirror image pair of CH2FCl. These are the requirements for optical isomerism. Number 1, carbon with 4 different substituents are known as chiral center. Number 2, no plane of symmetry in the molecule. And lastly, number 3, molecule is non-superimposable on its mirror image. The ethane model from previously is taken. One carbon is rotated. The spatial arrangement is changed due to different conformations, but it is still the same molecule. The rotation happens due to electrostatic repulsion between the CH bond electron clouds that causes fast rotation. Hence, the torsional strain is minimized. The rear carbon C2 is held, while the front carbon C1 is rotated until all CH bonds line up. The conformation of this is eclipsed. Then, the front carbon is rotated until 60 degrees, so each front hydrogen lies exactly between two rear hydrogens. The conformation of this is staggered. The rotation is continued until 120, 180, 240, 300, and 360 degrees. At 0, 120, 240, and 360 degrees, the conformation is eclipsed. The torsional energy per hydrogen-to-hydrogen pair is 1 kilocalorie per mole, and the total torsional energy is 3 kilocalorie per mole. And then at 60, 180, and 300 degrees, the conformation is staggered. The torsional energy per pair and also the total torsional energy is 0 kilocalorie per mole. Which is more stable, the staggered conformation due to lower energy, no torsional strain, and the hydrogen atoms are farther apart.
Next, for this part, we construct a molecular model of hexane. Upon observation, the molecule is not perfectly straight. This is because each carbon atom is sp3 hybridized, giving rise to a tetrahedral geometry. As a result, the bond angle between adjacent carbon-carbon bonds is approximately 109.5 degrees, which prevents the formation of a linear structure. By rotating the carbon-carbon single bonds, the molecule can adopt its most extended arrangement, known as the fully extended zigzag conformation. This conformation minimizes electron pair repulsion and represents the most stable arrangement of linear hexane. Therefore, each carbon atom exhibits a tetrahedral geometry, and the overall structure of hexane is best described as a zigzag rather than a straight chain. Then, the hexane model is joined to form cyclohexane. After the ring is formed, the carbon-carbon bonds are rotated slightly to reduce strain in the molecule. Based on the model, cyclohexane does not form a flat or planar ring. Instead, it adopts a puckered structure. The approximate bond angle between two adjacent carbon-carbon bonds is about 109.5 degrees, which is close to the tetrahedral bond angle of sp3 hybridized carbon. Compared to hexane, the carbon-carbon single bonds in cyclohexane cannot rotate fully because the atoms are locked within the ring structure. They can only rotate slightly. Therefore, cyclohexane forms a pucker ring to minimize the angle strain and torsional strain. Next, the cyclohexane model is twisted upward toward the middle by holding two opposite carbon atoms. This produces a boat conformation of cyclohexane. In this conformation, not all carbon-carbon bonds are arranged in a staggered manner. Some of the ethane, like carbon-carbon bonds, are eclipsed, which increase torsional strain. From observation, the boat conformation contains 4 eclipsed ethane-like conformations and 2 staggered ethane-like conformations. Therefore, the boat conformation is less stable because it has torsional strain and steric repulsion, especially between the flagpole hydrogens. Then, one opposite carbon atom is kept fixed, while the other is twisted downwards toward the middle. This produces the chair conformation of cyclohexane. In this chair conformation, all 6 ethane-like carbon bonds are arranged in staggered conformations. Therefore, there are 6 staggered ethane-like conformations and no eclipse conformation. Based on this observation, the chair conformation is more stable than the boat conformation because it minimizes torsional strain. It also reduces steric repulsion, whereas the boat conformation has eclipse bonds and flagpole interaction.